Welcome back to COS 217 lecture. I hope everyone's made good use of the time up until now to get acclimated to our environment in Linux and Bash on ARMLab, and has been able to complete assignment 0 making use of Git. Now we're ready to jump into the C programming language, and with that, assignment 1. After this lecture, you'll have everything you need to get going on that assignment. To start, we'll be talking about the history of C, its original design goals, and their implication on how the language turned out. This will be a continuing theme of the lecture content in the coming weeks. C came about here in New Jersey at Bell Labs, the research arm of AT&T and the predecessor of Lucent Technologies, which is now absorbed into Nokia. It was primarily a vehicle to build utilities in Unix, and eventually it served as the language for re-implementing Unix, the kernel itself, replacing an assembly language version. This was the first step towards a portable Unix environment. Dennis Ritchie was the inventor of C, and in his own words, in his book, The Development of the C Language, he had a retrospective that really fits well with the course's use of the language in terms of its mainstream success, its low-level access, albeit at the expense of portability, and its invitation for programmers to express themselves concisely. So his quotations are, C has always been a language that never attempts to tie a programmer down. It has always appealed to systems programmers who like the terse, concise manner in which powerful expressions can be coded. It allowed programmers to, while sacrificing portability, have direct access to many machine-level features that would otherwise require the use of assembly language. And finally, his takeaway famous quote is, C is quirky, flawed, and an enormous success. While accidents of history surely helped, it evidently satisfied a need for a systems implementation language efficient enough to displace assembly, yet sufficiently abstract and fluent to describe algorithms and interactions in a wide variety of environments. This really does sum up how we want to use it in 217. So C is a relatively old language, coming about in the early 1970s and having been unofficially standardized by the late 70s and officially standardized in the late 80s. There have been various additional language expansions and new standards since then, up through a couple of years ago, and there's a new one in the works. But they've tended to either be completely cosmetic, for example, how comments are defined, or focused on concurrent programming, for example, reentrant safety and threading efficiency. We intentionally choose to keep our class using the older version to avoid many of the complexities of the newer standards. They added some cognitive overhead in the sense that there are many more valid options to consider. And yet they didn't really add much in the way of the core language that we care about for our purposes in this course. So most students entering 217 know Java, and so for the rest of this part of the lecture, let's focus on comparing C's design and fundamentals with Java. Historically, C and Java were designed for very different purposes. C was used as a systems programming language for building a operating system and its tools, whereas Java was originally thought of as the next great language for the web, although that didn't turn out to be so great. The takeaways eventually from that is that C was designed without much of a care for safety. It was to be used by experts in creating these tools that were replacing tools that themselves were unsafe because they were in assembly language. Similarly, for portability, they were replacing tools that were completely unportable. Java, on the other hand, was thinking at least somewhat about portability and about safety because of its web desires. So a continuing conflict is going to be the safety and portability versus low-level access and speed, with Java largely representing the former and C largely representing the latter. In that vein, let's talk about the characteristics of C programs, starting with how we go from source code to runnable programs in the first place. Before we get into the details of C, let's step back, remember what we know about Java and how the programs in Java are built and run. So if we have a program, myprog.java, we're going to issue the command javac myprog.java. That invokes javac, the Java compiler, and it produces bytecode. That's a machine-independent representation of the program. Then Java C itself is a machine language code program. It's specific to a specific hardware and operating system. In our case, it's specific to ARMLab. It will read myprog.java as input and write myprog.class, the bytecode, as output. Then when we go to run it, we're going to issue the command java myprog. That invokes Java, the Java interpreter. Again, this is a machine language code program that's specific to our machine, but it reads in a class file that is portable. So in 126, you may have used Dr. Java or IntelliJ to issue those two commands instead of doing so explicitly, or you might have run those commands -intro cs. Again, we'll actually run those commands indirectly. Let's contrast with C. C executables, or executables made out of C programs, are built with the C build tools, colloquially called the compiler, but this term is not really true. It's really a synecdoche, as we'll discuss in a bit. They produce machine language code, not bytecode. So what's the difference? Let's see how they're run. Unlike with Java, where we had to run Java and our class file, here the machine code can be directly executed by the CPU. Whereas in Java, we had bytecode as an intermediate step. That bytecode wasn't runnable itself. It got executed on a virtual machine, and that was one extra layer of indirection. The extra indirection of the JVM adds complexity and potentially inefficiency, albeit with the benefit of standardization and portability. So we're coming to these same ideas over again in terms of the two very different ideals of these two languages that at first glance seem pretty similar. As the building and execution process sheds some light on the differences, let's look at a little bit more of the trade-offs between the two and the characteristics of C in the context of Java's equivalent of those characteristics. Note that the very end of this set of lecture slides has a detailed side-by-side breakdown of language features, though we won't cover them in point-by-point this lecture itself. They're there as reference. All right, so we said portability, let's talk about it. At the source code level, Java is theoretically completely portable. C is mostly portable, but less so, and we'll soon see some obstacles to portability. Below the source code level, Java bytecode is, again theoretically, completely portable. The Java interpreter's interface is consistent across all platforms, even when the implementation differs, insulating the bytecode from the underlying hardware. The machine language program myprog, though, is not portable at all. The machine language code is specific to a particular hardware platform and operating system. So in conclusion, Java programs are much more portable than C programs at both the source code level and especially below. The other characteristic we mentioned was safety and efficiency. So portability was a clear win for Java. And we'll see the same for safety and convenience, like bounds checks and garbage collection. There are a lot of nice features in Java, but they do come at a cost: speed and predictability. Think about Java as a language for embedded systems. You're driving your awesome high-tech car with its adaptive braking system, and just at the moment when you slam on the brakes, your brake controller decides that's a great time to go clean out all the memory that it can figure out it will never use again. Of course, the counterpoint to this one in C is that C might be super fast, but if you never free any of your memory, it will eventually run out and you'll crash, in this case, perhaps literally. So these are both design decisions. There's not necessarily one right way or one wrong way, but they must be taken into account in terms of the uses of the language. So here are the C equivalents. We have manual bounds checking and manual memory management. Note that we list null pointer checking in both of these, but in both cases the check results in just a crash. So it checks it for you, but if it doesn't like what it sees, the program crashes. Contrast this with bounds checking, where Java crashes, but C does something even worse. It doesn't check and it just keeps running, probably in an incorrect state. So again, safety, probably a win for Java. Efficiency, though, all of these have a cost, And all of these checks, all of these system state verifications and system state processes like garbage collection where it does it for you, well, that has a resource cost. Typically, we can assume that C is going to be faster than Java. So they are nicely complementary, and they're both good choices to learn in some of your first few programming courses. So thinking about their differences, take this analogy. Which car might you consider to be C as opposed to Java? Take a moment to make your choice. Pause the video, say it out loud, or write it down for accountability. So a number of people are likely prone to put A, the old rusty truck. And yes, C is old, and it's not particularly modern, and it's definitely not portable, which that truck certainly isn't as well. So it's not a bad answer. But C does still run and is widely used, which that truck certainly isn't. The Volvo also isn't the right analogy. Volvos are traditionally the safe car. They pioneered three-point seatbelts in the late 50s, and they're sometimes thought of as boring. The mom wagon here certainly fits that. Personally, I love my S60, but that's neither here nor there. So if anything, this is Java, not C. So that leaves B, the souped-up car. It's a little faster at the trade-off of being a little riskier. This is C, at least compared to Java or similar languages. And so if C is your hot rod, let's get programming. As a warning, the rest of this lecture is quite fast-paced. Brace yourself. It's throwing everything at the wall that you need for assignment 1 and hoping enough of it sticks. But as reassurance, there will be more systematic coverage of C to follow, both in lectures and in precepts. So the remainder of this lecture will be based around 3 little C programs that serve as our initial examples of the language, and again, will set you up to make progress on assignment 1. Our first program is charcount. It's equivalent to the WC program that you saw in the Linux and Bash overview when invoked with the -C argument to count characters. You'll see a larger version of this program again later in the course when you implement it yourself in assembly language. So what's the output of charcount on this input? We run it and we type into standard input line 1, the return key, line 2, the return key, and then we send it the signal to say I'm done with standard input. Take a moment, pause the video, make your vote, and say what is the answer here? Well, on line 1 we have LINE space 1 and then the new line character. So when you hit return, it's actually inserting a character called new line into the stream. So that's 7. Line 2 has LINE, the space, the 2, and the new line character. Again, 7. EOF, the signal you send to say I'm done with input, isn't itself a character. So that means that we have 7 and 7 makes 14. And as promised, this jives with WC minus C. So here's the program code. Take a quick look at it. Some lines will look very familiar to your Java-attuned eyes. Others might look quite foreign. But it's okay, we'll break it down almost line by line. When you ask the shell to run an executable, it loads the machine code generated by the build system, which conventionally starts with a runtime system that has some basic starter code that we call _start. _start, then its primary job is to call main. So for the code we're writing, execution starts at main. This is just like in Java in that sense. But note that whereas in Java you had public static void main string brackets args, in C it's a lot terser. We'll learn how to replicate some of that Java verbiage later in the course, but for now, we've just got a simple main method that takes no arguments and returns an int main void. So coming into main, this looks like the variable definitions that we would expect from Java, except C is an int, not a char. That's a weird thing to look at, int C, when C means char. But the reason here is that our function that we're going to fill C with, getChar, returns an int, not a char. You might naturally ask a follow-up, okay, then why that then? The reason here is that we want to be able to identify any valid character, while also identifying whether we failed to read a character at all. That means we need more space than just a char. If any valid char could be returned, we fill up all of our possible values of char and still don't have a way to indicate that we failed to read a char at all. Thus, we should assign the value returned by getChar to an int because it returns an int, because it needs that one extra value to say, I'm not giving you back a char, I couldn't do it. If you assign the return value into a char, that can cause trouble because it's not necessarily clear whether you've read in the value associated with I couldn't read a char, cast into a char, or that character itself. We'll see this in more detail later. So getChar is a function from one of the standard libraries. Our program knows about its existence because we've pound included a header file. We'll talk again more about this in just a minute. As mentioned on the leading example, there's no such thing as the EOF character. EOF is just a number defined in a header. It is that value that says, I could not read a char. Perhaps there's a better way to think of this than EOF, which stands for end of file. You might call this read failure or end of input or something like that. On our system, EOF is defined to be -1. It's in that stdio header file, but we don't actually need to know or care about this. We just use EOF as the semantically meaningful constant. At this point, we get to the loop, the core of our function. And we use the result of the priming read just before and compare if we read a valid character or got that non-character status back from getChar. If we read a character, then we increment the count to match. After doing that increment, we're going to call getChar again to replicate the priming read and set back up for the loop sustaining condition. Eventually, we will run out of standard input and getChar will fail. That is, it will return EOF. That should end the loop. And so after the loop, we print our result using printf, which is not unlike the system.out.printf or standardout.printf that you're familiar with from 126. Finally, we return. Returns work the same way they do in Java. They return to the spot where this function was called from, sending back a value if the function isn't specified as a void return. Main's calling function, as we mentioned before, is _start, which means that when we return to it, we're going back to _start, and really all it does is just cleans up any state that it set up for main, and then immediately exits with the same exit status that main returned. We talked about exit status in the Linux and Bash lecture. The C standard says that a program that succeeds must finish with the exit status 0. That accords to what we talked about in Linux and Bash. The C standard says that any program that fails should finish with the exit status exit failure. But that value exit failure is system dependent. On our system, it's 1. The values exit success and exit failure are defined in stdlib.h. So here we return 0, just the literal, but we could have pound included stdlib.h if we wanted to use exit success as a semantically meaningful constant for 0. All right, so that's the program. We saw earlier at the high level the difference between C and Java building their program files. But that discussion earlier was focused on the fact that GCC creates an executable, not bytecode. Now, having a program to use as an example, we're ready to dig in and build a C program in a little bit more detail. And we'll see why calling GCC the compiler is not quite the whole truth. On this slide, you can see the shortcut command, which is the default. It completes all stages of the build process, starting from the source code and ending up in the executable, all in one invocation. With the -o option, the next argument is the executable name. And without the -o option, the executable will be named a.out for quirky historical reasons. Note that in Linux, as mentioned in a previous lecture, file extensions are only for human readability and aren't typically given to executables. We could call it charcount.exe, and that would have no greater meaning than charcount.out or charcount alone or charcount.any string up to the total file name limit, which is 256 or 4096, depending on settings. So we actually run the charcount executable by invoking its name. Recall from the last lectures that // says find the program here in this directory. So charcount reads the characters from standard in until it reaches EOF. The story for how to get EOF is just what you're used to from Java. In 126, by default, standard in is bound to the keyboard, and so we can indicate EOF by Control D. Again, noting that EOF was badly named, so if it's bound to a file, we don't actually have to send it Control D. EOF will be reached when the file is done. A few more brief reminders of some things from 126 in the earlier lectures. We can redirect standard input, reading from some file instead of typing at the program. And we can redirect standard output, having the program write to a file instead of writing to the terminal. So for illustration, now let's perform each step individually. We said that the build process was more complicated and there was this shortcut that would perform all the steps. Let's look at each step one by one. Note that this is as required for assignment 1, and I'm moving quickly here, but you'll get an overview of these stages, but you'll also see them in more detail in Precept, the second Precept this week. Alright, so we start with the initial program we saw before, written in C. There's no indication whatsoever of what get, char, and printf are. The grammar makes it so we know their functions. That's literally all we know. We don't know if they're used correctly, we don't know what they do. So the first stage of our 4 stages of building is the preprocessor. It's invoked with -E, which nobody ever remembers, but I like to think of it as E for extra stuff. That's because the preprocessor puts some extra stuff into your source code. And by convention, it produces a file with a .i subject and a .i suffix, so you can remember that as having done the pound includes. Because what it does, it removes some comments, and it handles the preprocessor directives. These are, in our case, pound includes. Let's look at that. The preprocessor first removes comments from the source. They're of no use to the compiler, only to a human reader, and so they can be discarded. Incidentally, if you haven't looked yet, this job is the crux of assignment 1. Next, the preprocessor handles preprocessor directives. These are lines beginning with the pound sign. We'll see several of these throughout the term, but again, here's our first, pound include, which indicates an interface that the program relies on. The way the pound include gets handled by the preprocessor is to replace that one line with the entire contents of the file ctype.h, plus some metadata markup. Note that this new content is really an information dump to the compiler, telling it the details of a whole bunch of symbols, like functions and constants, that are available in some other interface. After the pound include additions, the preprocessor next does a scan to replace all the macros, which here are used for symbolic constants. With the values, they replace it with the values they represent. So EOF here is actually a macro defined in stdio.h, and it gets replaced to be -1. Alright, so this is what we have in the .i file. It's still the C language, approximately. There's some markup there. And we can also see another use of why we're using an int as getChar's return. There's no character -1. On our system, chars are unsigned, and the smallest value then is 0. If we were to give -1, it would overflow. It would go from 0 back to the highest possible char value, and thus it wouldn't be unambiguous. If we put a char there, we would say, well, do we mean the highest value char, or do we mean -1? It wouldn't be clear. That's why we use an int. We can also see how the pound include worked out. These lines at the top are declarations. They're messages to the compiler about the existence, somewhere, of a symbol. Think of this as, hey compiler, getChar is a function, it takes no args and returns an int. This allows the compiler to then eventually type check and make sure that it's used correctly. So we said the compiler, that's the second step in the build process, compilation. Compilation is a translation from C to assembly language. The invocation is with -s, and my mnemonic for that is primarily just the fact that we actually will write assembly language in this course and put a .s suffix for it. But you can also think of s as syncing to a lower level language. It's our first lower level descent. So these three declarations, these two declarations are, remember, the love notes from the preprocessor to the compiler telling it that getChar and printf are a thing. and that means the compiler can verify that any calls to them type check correctly. The compiler then translates progressively. It starts off and says, can I generate assembly code indicating the definition of main? Inside the block, aka compound statement, the compiler will generate assembly language code to allocate space for variables, and then instructions for completing the rest of the block. Note that unlike in Java, in C89, declarations must appear at the top of a block, not within the body of the block after some other code. This is also where the compiler uses the declarations to complete the type checks, because it sees a call to getchar and it sees a call to printf. And so it can check and make sure that the calls have the same type it was expecting from the declaration. Alright, so the compiler is just a type checker and a syntax checker of C code that then translates from C to assembly. Note that at this point, the getchar and printf are still just symbols that we've been told are functions, but we still don't have their actual code. After the compiler comes the assembler. The assembler is just another translator, this time to translate from assembly language to machine language. Note that it's a common terminology trip-up to think the assembler must generate assembly, but that's not the case. The assembler takes assembly and generates machine code. If you've been enjoying, as opposed to groaning at my weird mnemonics for the GCC options, this time I like -C for can't read that anymore. Because, indeed, at this point we have machine language, which is just a bunch of binary. We can't read it anymore, although stay tuned, by the end of the course we will in fact learn to interpret some small set of machine language and their instructions bit by bit. And so here we have just a bunch of binary, and yet still at this point we still have no idea where getchar and printf are. We just have the machine language code to call them. We don't have their code itself. We better find them soon, because this was step 3 of the 4-step build process. So finally, the fourth tool in the build process is the linker. The linker's job is, again, finally, to go and find the as-of-yet unresolved machine code referenced in the program. In this case, both getchar and printf exist in the standard IO standard library, which on our system is shoved with all the other standard libraries into an archive file living in /user/lib. So it will go and find the correct code from that library archive and slurp it into the final program. After the linker runs, we have everything we need. We have a complete executable program. That's the build process, and for the first several assignments we're going to ask that you complete each one of these steps separately so that you get a sense of what all is going on under the hood when you just magically type GCC 217. Before we move on to the second of our small programs, pause the video and take a moment to consider if there's a better way to structure the body of our char count program. Note that D here is the existing code, just with weird pagination so I can fit my face in the corner. Pause the video, see if you like one over the others. So this is a judgment call. Looking at each of the options, A and D have getchar in 2 different places. That's a little bit weird. C has an infinite loop and a break statement. Some teachers, especially high school teachers, go crazy of, no, you must never use break. There are better ways to structure a program. And B has this cryptic assignment statement inside a loop condition. B is, in fact, the most idiomatic C. Albeit some people might say that it's the most idiosyncratic C or the most unreadable C. I do tend to like B best. Next, I would choose D just because I tend to dislike for loops where you don't have a mathematical expression for how many times the loop will execute. But really, all of this is judgment and personal style. All right, our second program is going to be one that uppercases all of its input. Maybe we could call this Shoutify. To compose the program, you must know how to identify lowercase characters. That motivates a discussion of how characters are stored. Each character is stored actually as an integer, just a really small integer. And the computer system's character code maps each character to a unique integer. Our system uses ASCII for 1-byte characters, which is generally a good assumption on most modern computers, but is in fact not the only option. So take a look at this first version of the program. We declare our int c, again an int because we're storing the result of getChar into it. We have the cryptic, idiosyncratic, idiomatic, take your favorite word for it, while loop with the assignment statement. And then we have an if statement with 97 and 122 and 32 all built in. Something should jump off the page from 126, what you've learned, and that is that magic numbers are hard to read and interpret. Worse, these magic numbers are ASCII codes, so not only are they hard to read and interpret, they also present a problem for portability. ASCII is pervasive, but it's not ubiquitous. This wouldn't work, for example, on a system that uses another encoding, EBCDIC or other things like that, because the values are hard-coded. The algorithm itself wouldn't work for any encoding where the lower and upper cases aren't 32 characters apart. And there's no reason they necessarily need to be, so that's a pretty strong assumption by the algorithm. So we can get around these magic numbers by using character literals, which, like in Java, are indicated in single quotes, with some special characters indicated by escape sequences starting with backslash. So here's our second version. It uses character literals, and it's better than the previous version because it doesn't assume ASCII. It does, however, do this weird thing where it does arithmetic on chars. In C, I said a char literal is identical to a char variable. It's just a number, a very small int. So on ASCII, a, lowercase a, is identical to 97. Thus, we can subtract things from it. We can do greater than or equal to with it, and that's totally okay. Incidentally, on the other system I mentioned, EBCDIC, the lowercase a is 129. Again, showing that we can't just assume the values themselves, but we do get around in both of these by using the char literals. So, arithmetic on chars, totally okay. But what's wrong now? Well, it still has the other problem I mentioned. It assumes that the numeric codes of uppercase letters are at some constant offset relative to the numeric codes of the lowercase. Okay, it doesn't have to be 32 here, that's better. But what's to say that they're a constant offset at all? It assumes that they're contiguous, which isn't true for EBCDIC, and it's really getting complicated fast. If we wanted to make a general purpose here, there's a lot that we can do. There's got to be a better way. And there is a better way. Hey look, a man page. There's a library for that. The library here is ctype.h, and the advantage is that you know the standard library has been configured for the machine you're running on. Along with the is functions that were on the previous slide to identify whether a character is a member of a class, we have the to functions to perform a transformation on the character. So if we're trying to shoutify, the natural thing we want to do here would be to pair is lower with to upper. So here's what that turns out to be. A quick refresher of the previous program. What would happen if we omitted the pound include of ctype.h? Pause the video, answer it, say it out loud, commit yourself, and then restart. If we omit the pound include of ctype.h, the compiler will generate a warning when it encounters the call of is lower and to upper, because it says, I've never been told these things exist, so I can't type check them. It's not going to generate an error, though, because they might actually be findable by the linker. In this case, they're from a standard library, the linker can go and find them, and so the build will succeed without error. But we do want to have this pound include so that the compiler can find earlier if we've made a typing mistake, and also because generally printing out lots of warnings seems unseemly. All right, one more brain teaser for this code, but I'll spoil it immediately. So is the if statement really necessary? The correct answer to this question is, I don't know, let me go look up the man page. So over here on the man page for to upper, the return value section says that to upper doesn't change a character that isn't lowercase. So now let's come back to the full question. Is the if statement really necessary? Pause the video and decide for yourself whether this is necessary for correctness, not necessary but you'd leave it, or not necessary and you'd get rid of it. So from the man page, it's not A. It's not necessary, because if it's not a lowercase character, 2upper isn't going to do anything to it anyway. So A is not the correct answer. B versus C, as we're seeing as a trend here, is a judgment call. B is arguably less mysterious. C is potentially faster since there's one fewer function call and one fewer conditional branch per loop. But really, up to you. I'd probably choose B just because just 2uppering everything, now you're relying on someone reading your code to go and read the man page. And as much as I'm pushing, read the man page, read the man page, read the man page, I know you're not going to read the man page. So we can put it in the code at the cost of just a few cycles. All right, finally, let's look at a third program, which will give you a sample of pretty much every C language component that you'll need for assignment 1, and even better, the overarching design of your program. Our third program will be to capitalize each word rather than each letter. Let's define a word for simplicity as a series of characters delimited by white space. That's a fuzzy approximation of English language usage without, no pun intended, language lawyering about what exactly is a word versus not. All right, so to design this program, we're going to need to decide for each letter whether we should capitalize it or not, choosing to do so only when it's at the beginning of each word. This sounds like a COS 126 exam problem to figure out a regular expression for what letters need to be capitalized. But if it's a regular expression, then, well, we can build a DFA. Thanks, Stephen Cleany, class of 34 grad. All right, a quick refresher from 126. A deterministic finite automaton is a computational machine that processes a string in order, only considering each letter in the string once, by transitioning between states with each subsequent letter of the string. In 126 and in assignment 1, each state will have a status that indicates whether it's an accept or success state or a reject or failure state. And that applies only if the machine halts in that state. It's not that when you reach an accept state once, hey, it's successful. No, every state will be either accept or reject, and it only matters when the machine halts. All right, so for this problem, though, we don't really have a success or failure criterion. We're just completing the action for each character. So we won't label any of the states as either accept or reject. All right, so thinking about an algorithm using this DFA, we start over there in normal. So long as it isn't an alphabetic character, we haven't started a word, so we're just going to print it out. Once we hit an alphabetic character, that's the beginning of a word, so now we need to uppercase it. But from now on, we're inside a word, so we should transition to the other state, and in that state, each character that's an alphabetic character, we're just going to print it unmodified. Eventually, in that other state, we're going to read in a non-alphabetic character, in which case we say, aha, that's the end of a word, so let's transition back over into the normal state. We'll print out the non-alphabetic character, and now we're in the normal state, waiting for our next word to begin. So we continue this until we run out of input. That's the general algorithm. Let's see how this shakes out in code. Here's a first crack at a coded up version of the DFA using an int to represent the state. Because of this design choice, I see a whole bunch of zeros and ones and no real sense of which either means. I mean, I know I used to have normal and inward. Well, which is which? I could go back and look and say, okay, which was the default state? The start state was normal, so 0 is the default here, the initial value of state, so 0 must be normal. But really, there's a better way. We can do better. We should aim to fit the program to the well-specified and clear original DFA, which did use those semantically meaningful names like inward. And we can do so in C with an enumeration type. An enumeration type, or just an enum, allows you to specify your own named integer constants, either explicitly, or since we don't actually care what the values are here, 873 and 4126 are just as good as 0 and 1 for our purposes, we could do it implicitly. On this slide, we actually have it implicit, but actually, conveniently enough, when not defined explicitly, C will start at 0 and advance by 1 more than the previous enum member each time. So this code will give us 0 and 1, just like the hard-coded version did. All right, so here's our program enumified to remove the magic numbers. It's better, but there's still a problem here. What's wrong? Feel free to pause the video and see if you can identify something that's not so great about this code. So this is getting pretty deeply nested. We're going farther and farther over to the right side. Perhaps it's not the end of the world for this two-state case where each state only has a single if-else, but what if there were more complicated logic to handle in each case? And what if the number of cases exploded? The cases here represent the different states in the DFA. That switch would get awful really fast since there's no modularity. The solution to no modularity is, and I know this will shock you, modularity. In this case, if we're concerned that sufficiently complex logic to handle any one state will become a problem, we can push all that actual logic into one function per state and make the switch statement just a minimal framework. It just says, which function should I call? Call it. Let's take a look at what that looks like. Our code is getting longer here as the modularity has some overhead of extra functions to define, but that's okay. Lines of code do not mean that the program is worse. Our main now has that minimal code in each switch case, a call to the function that does the actions associated with the current state and the input character, and then it takes the function's return and sets the new state, and then a break that isolates the cases. This is pretty good. But if I handed it to you on an exam, how long would it take for you to figure out what it does? I'm sure it would be better if it had comments describing the different pieces. So let's call this the A-. Admittedly, this is nitpicking since we've been omitting comments this entire time from our examples just to fit it on the slides, but it won't be nitpicking on your assignment code, I promise. Alright, oversold or not, this does serve as a convenient segue to talk about our internal documentation requirements. That is, what comments should you put in your code? So function comments should describe the behavior of the code from the caller's perspective. What does a caller pass it? What does the function do? And what does it give back to the caller? These comments are the ones that would be appropriate for an API and thus shouldn't reveal the function's implementation details. Here's an example for you to chew on for a second. Feel free again to pause the video so you can read the two comments in full. The first gets too far into the weeds about interaction with the other functions that the caller doesn't even need to know about, as well as the internal design of that function. It's barely one step short of saying, this function uses a while loop. The latter, on the other hand, lists only the pertinent information, what global state the function affects, the standard input and output streams, what the function computes from its parameters and input, and what value it returns. This is exactly what a caller of the function needs to know. The next 4 slides are a complete version of the program having fixed the suite of issues from previous versions. Once you've written your DFA for assignment 1, you can use this code as a great jumping off point for implementing the DFA structure in C code. Alright, so I promise that you'll get a long way in A1 by designing your program to mimic the final version of Upper 1, just expanding it for a more complicated DFA that you'll need in assignment 1. So I leave you by encouraging you, start assignment 1 soon. It's due Thursday the 17th, that's a week and a half away, but you now have everything you need in order to complete that assignment.